we were trying to solve the heat transfer from the iron base plate and as well as the variation of temperature inside the base plate. And we have determined that for the steady state case and no thermal energy generation, and for 1D heat transfer, we have this temperature variation inside the iron base plate here. The temperature will be linear. And to find the values of C1 and the C2, we need two boundary conditions. And the one is that at the inlet it is conduction, and at inlet I mean here. Here it is conduction, and here it is by convection to the environment. So I have written it here. Now let's solve this problem. And for the first part, and x distance is this one, and I can just write that at x is 0 and the q cd, you will have that q dot cd, which is in the amount of the, let's see, 100,000 q dot cd. It will be 1800 watts actually, 1800 watts. And now let's just write the equation of the q dot cd, and the q dot cd will be equal to negative k a and the dt by dx. Okay. And this one will be negative k and the area dt by dx. So you can see it here, the derivative of t with respect to x will be just c1. And so this one should be calculated at x is 0. So that I can just know that at the x is 0 here, it should be x as 0, but you can see that the final result, which is C1, is independent of the x direction. Therefore, no need to put x 0 here, because C1 is constant and it is independent of the direction of x. And this one at x is 0, it should be equal to 1800 watts. And you can just replace the values here. For example, the k value is given as, and K value for the material here, iron plate. So K value for the iron is not given, but I think you should have the table for the metals. So this one will be at the previous slides. Anyway, so you can find the K value for the iron here, and the area of the plate is given 340 centimeters squared. Okay, and that's all. Say that the K value is, for example, how much that is 100. So this one is 100 watts per meter squared Kelvin. Okay. So if that is the case, iron plate, so you will have the values here, and you can just calculate the C1 value. Or for general expression, for generality, so you will have that C1 is equal to 1800 watts and divided by negative K and A. Okay. This one will be the value of the C1. Okay, so now comes the second value, which is the C2 value. And to find the C2 value, we'll use the convection boundary condition at the outlet. Now let's use it. Okay, to find C2. Okay. And at x is L here, you have the convection heat transfer. And if you remember, we have said that for x is L, this one is interface. And for the interface, if you remember from our previous slides, we have said that interface cannot store energy. So it transfers whatever energy is incident on it. So here for the interface, you will have that Q dot CD will be equal to Q dot CB. Or if you write in general form without any, that. So here you don't consider the area. This one is flux, and this one is the rate of energy transfer. Okay, so what it means is that here you have this one is metal. From this metal you will have the conduction here, Q dot CD, and that conduction will be removed from the iron plate by convection, Q dot CB, because the iron base plate, you can see it is exposed to the room, and the room will have some convection coefficient and some temperature, and therefore you will have this boundary condition at axis L. Now let's solve it. First, the conduction heat transfer, it will be that negative K A and the dt by dx here, but it should be again not x is 0, but it should be x is L. It should be equal to and H, AS, and the T at L minus T infinity. Okay. This will be the convection part. So when X is L, conduction is equal to convection. And the convection part is easy because it is Ka, and instead of dt by dx, you can just write the C1 here. Again, as I said, the C1 is independent of the x direction, therefore no need to put this x is L here again. But this is independent of the x. It will be equal to H and the surface area here, and area is given in the question. And instead of TL, you can just write that, so that if you remember from our previous part, T is C1x plus C2. That here, so T is C1x plus and C2. Okay, and if you just put that x is L here, so it will be that T at distance L will be equal to C1L plus C2. Okay, and this one will be just C1L plus C2. This one is for TL and minus infinity. Okay, so the C1 value, it is found from the previous boundary condition, and the C2 value can be found from this equation here, because all of the values are given. You know the K value, which is 100, you know the area, and you know the C1, and the H is given in the question as 20, and the area is also given, and you can even cancel out these areas here. And the C1 and again is found, and L is given, and the C2 and the T infinity. And the L value is here, that thickness is 4 millimeters. Okay, so it means that here you have the x is 0, and here you have the 4 millimeters. Here x is L, and that is 4 millimeters. So by this one, you will find the C1 and the C2 value, and from the C1 and the C2 value, you will see what is the temperature at the base plate, beginning of it and end of it. We can find the temperature variation here. We have one more question here. So that the question is that we have the steam that flows inside a pipe, and with an inner radius of 6 centimeters and a thickness of 2 centimeters, and the length of the pipe is 20 meters. Show the temperature distribution inside the pipe thickness for the given values. Okay, so that the values that are given in the question, and you know that are not important, because at the end you will have the general expression, and for that general expression you will find different values depending on the question. Okay, but for the completeness of the question here, we have just given the values. Okay, so let's find it. So that again we'll use some assumptions, so that our approximations will be. Okay, so the first approximation is that it is 1D heat transfer. 1D means that, so that Q dot is only in R direction. So if you remember, we have said that you will have the Z direction here, you will have this R direction here, and along this circumference you will have this theta direction. Okay, and here we are only assuming that heat transfer happens only in R direction. And the second one is that it is steady, and the third one is that it is no thermal energy generation. Okay, now let's solve this problem now. So what I will do is that, so we just draw the pipe here one more time, and for this pipe, so this one will be the center, and at a distance of R, I will take a circumference of this one, and at R plus dr, okay, so this one will have a circumferential length of R plus dr, so that radius. So, okay, then this one will be my control volume. This one is our control volume, and for this control volume, I will just write the energy balance. So now you will have the energy balance for the selected part here, selected control volume. So that just let's write it. So you will have that Q dot at R. This one will be actually the energy one. So that Q dot at R will be equal to Q dot at R plus dr. And again, we will use the Taylor series here. It will be that Q dot at R and plus that del Q dot about dr and multiply it with this dr. And from this one, you will have this cancel out, and del Q dot by dr into dr will be equal to 0. Okay? And dq dot by dr will be equal to 0. That heat transfer doesn't change in our direction. So it will be that heat transfer is constant in our direction. Because its derivative with respect to r is 0. If it is 0, that means that the heat transfer doesn't change in our direction. Now I will replace the Q dot formula so that Q dot was equal to negative Ka dt by dx. But in radial coordinates, it will be that negative Ka and dt by dr. Okay. Now let's go back to here, so that here the conduction heat transfer happens. If I just show it for you again one more time, this one is the pipe flow. And in our direction, so in that direction, the heat transfer for conduction is the surface area of the cylinder. For example, this part. So this part is where you have the conduction heat transfer. So that area is 2 pi r and into L. Okay, this is the area, so 2 pi r into L, the surface area of the cylinder. So this one is where you have the conduction heat transfer. So in the similar manner, similar logic, I will just write it here. So then you will have that del by dr here of that negative Ka and the dt by dr should be equal to 0. Right, this is the equation that you are going to have here. And just I will do that dr here. Instead of that area, I will just write 2 pi r and into L and the dt by dr. Okay. That will be equal to 0. And this will be the conduction heat transfer for the cylindrical coordinates. But as you can notice that the r coordinate here depends on the radial dr coordinate. And you can just integrate and these quantities here, and let's do it. So let's first define that K is constant here, this one is constant, and the 2 pi is constant, but R value is, it is variable and depends on R. Okay, and the L is constant here, and dt by dr is, again, it is variable. So if these are constants, I can just write that negative K and the 2 pi L, and you will have that dr, so R dt by dr. It will be equal to 0. And these are all constant, therefore just, so you know that right hand side is 0, so that you can divide by these terms, and at the final result, you will have that dt by dr is 0. And integrate it, you will have that R dt by dr is equal to constant 1, and the dt by dr is C1 by R. And the temperature here will be, if you integrate it one more time, so you just divide it by R, and if you integrate this quantity by one more time, you will have that C1 ln R and plus theta. That is the temperature variation inside this pipe thickness. So you have to remember that this is not about the pipe fluid here, it is all about the pipe wall. This is all about the pipe wall. This is conduction. Okay, we have only worked with conduction equation. So for this pipe wall, if you look at the cross section of this pipe wall, for that cross section, you will have some thickness here. So this is the pipe, and this pipe will have some thickness here. this amount. Okay, this is the thickness. And the temperature variation here. Okay, so here you have the T variation and the temperature variation is in this form. Okay, the temperature variation inside the thickness here, this one should be solid. Okay, so we are not considering this part and we are not considering this part. Only the part that is solid is the part that we are analyzing, because we are looking for the conduction heat transfer. And for the conduction heat transfer, the material cannot move, for example, like fluid or gas, etc., liquid or gas. The material should be stationary for the solid case here. Okay, so with this in mind, so we have found that T is C1 ln R plus C2. Again, what we need is that we need to that boundary conditions. Two boundary conditions will help us to determine the value of C1 and the C2. And then I will go back to the question here. The question says that that inner surface is 150 degrees Celsius and outer surface is 60 degrees Celsius. So the question says that here, where the pipe thickness starts, the temperature is 150 degrees Celsius, and here you have 60 degrees Celsius. Okay. I will just replace the values here and define the temperature C1 and the C2. Now let's do it. So that at R is our inner, that this one is center here, and you will have that inner radius, so that R inner. When the R is R inner and the temperature is 150 degrees Celsius, and I will just replace it here, so that 150 will be equal to C1 into ln R inner. Inner radius is 6 centimeters, so it will be that 6 times 10 to the negative 2 meters and plus C2. This is the first boundary condition. And the second boundary condition will be that when R is our outer surface, so you can see it here, outer surface is 60 degrees Celsius. So I should find the outer radius here. And this one will be equal to that inner radius, which is 6 centimeters, and plus the thickness of the pipe, which is 2 centimeters. So that R inner plus 2 centimeters. It will be 8 centimeters. So at R is our outer, and the T is and our outer is, I should note it's 8 centimeters. 8 centimeters, and the T is 60 degrees Celsius. And therefore 60 will be equal to and C1 ln, and instead of that 6, you will have that 8 times 10 to the negative 2 plus C2. Okay. These are the equations that we need to solve it and to find the C1 and the C2 values. So if you have any questions, you can ask. Otherwise, I will summarize this chapter and then move on to next chapter, which is the steady heat conduction and the resistance concept. Okay, that I will take the just summary here, so that we have looked at the 1D case, no heat generation, and the steady heat conduction equations. Okay, so that this one was the simple approach to heat conduction equation. But in general, in reality, you will have the 3-dimensional heat transfer. Okay, and the no heat generation, the heat generation part is not so well known, it's not so common, but the steady part is also will be unsteady. Okay, but we have only looked for that general simplest case, and the simplest case, and one was for the plane wall. Okay, and for that plane wall, the temperature has become that C1x plus C2. This one was for the plane wall, and we have also looked for the cylindrical wall. And for that cylindrical wall, and we have found that the temperature is equal to, let me just go back to our previous slide here. So C1 ln R plus C2. Okay. This one was the cylindrical wall. And you will have also the spherical wall, and you can find the temperature variation for the spherical wall by yourself. Okay. And as I said, this one is for the simplest case. And another is that simplest approach about the plane wall is that here, that area is constant. So if I go back to here, let me just go back to the wall case here. You can see that when Q dot is X, so at this part, area is AX. Then Q dot is X plus DX here, and the area is X plus DX. Okay. And the area at X is equal to area at X plus DX. Okay, because this one is the height and this one is the width. And that height and the width combination doesn't change when you move in X direction. Okay. And for the plane wall, area was constant. In other words, area at X was equal to area at X plus DX. But for the cylindrical wall, that is not the case. If I go back to the cylindrical wall here, for this one, you can see that area at R and the area at R plus dr, they are different, okay? Because area increases in I direction. So for area at R, you will have that 2 pi R and into the L, and the area at R plus dr will be equal to 2 pi and R plus dr into L. You can see that area increases in R direction, okay? And therefore, here area is not constant. So that A not constant. Because area at R is equal to 2 pi RL, and the area at R plus dr, you will have that 2 pi R plus dr into A. And that is the reason that you will have this complex function where the temperature depends on the radial coordinate R in a logarithmic manner. You can see that by the variation of the area, the temperature has become a bit more complex. That depends on the logarithmic function of the R. This one was the most important case for this chapter. And also for this chapter, I've looked for the graphical method of the heat transfer. And for this graphical method, you have said that you have two lines, and one is that isothermal line, and the other one is that adiabatic line. Okay. Just let me summarize this part too. And we have said that you have that isothermal line and adiabatic line. And this adiabatic line, this one, it's also called heat flow line. And we have said that so you have that temperature is T1 here, and the temperature is T2. And where you have that T1 is greater than T2. And due to that temperature difference, that heat will flow from this one to that one. Okay. And these are the isothermal lines. If I draw the adiabatic lines will be perpendicular to that isothermal lines. So these are adiabatic lines or heat flow line. But these are the T1 and the T2, these are isothermal lines. That heat flows from first isothermal line to another one, but in a parallel manner to adiabatic line. It is very similar to traffic flow. And for the traffic flow, what you will have is that you will have the lanes here. Okay, so you have the lane, and these lanes, you can see that these are very similar to the adiabatic line. And inside that lanes, you will have the cars that are moving. So that here we'll have the car that moves, and here you will have that car moves. Okay, and these cars are moving from velocity of v1 and to velocity of v2. Okay, you will have a change of velocity from v1 to v2 of these cars, and they are moving in a parallel direction to this, you know, that the borders along the lanes. Okay. Similar to here, you have the adiabatic lines, and in between these adiabatic lines, you have the lane, and inside that lane, you have the heat flow from T1 to T2. Okay, that is for the summary of this chapter. Okay, so that with this one, I finish this chapter, and then I move on to next chapter, which is about the resistance concept in heat transfer, and it will be all about the steady heat transfer conduction. And now let's just go back to the next slide here. Okay, so that series resistance concept. So firstly, I will talk about that one, and then I will talk about the parallel resistance concept and the radius of insulation and contact resistance. Firstly, we have to remember from our previous lecture that we are continuing with the same concept here, but in a resistance manner. So that in our last lecture, if you remember, we have said that it should be steady one-dimensional, and no thermal energy generation. Okay, this chapter, so this all will be that resistance concept, and this resistance concept will be applied for the 1D and the steady, no energy generation. Okay. So it is like that we are continuing to the previous lecture, but in a different manner, which is called the resistance concept. Now you will see slides what the resistance concept means. Okay. So first I will start with a plane, and again I that just written the approximations here, and you have one more additional that here you have the constant area. Okay, let me just start with the steady case. As I said, the temperatures. So let me just show the temperature values on one side of the wall here. Let's say that here you have that is T1 here, and here you will also have T1. If I go another point here, you will have that T1. If I go here, and you will have that T1, and here you will have that T1. You can see that the temperature along this surface here, so that also that the points that I'm not able to show you, the temperature is always T1. Okay, and this T1, these ones, doesn't change with respect to time. Okay, because it is steady, and it is same along that surface. It is same over that surface. Okay, so here you have the always T1 here everywhere on that surface, and that T1 is constant and doesn't change with respect to time. Okay, this part where it doesn't change with respect to time, it is about the steady case, and same over that surface, it is all about the one-dimensionality. Okay, now if I go back to the next surface here, so here, and you will have that T2. If I go next point here, T2. If you go in a random point, you will have that T2. Let me just put it as T3 and the T3 and the T3 here. If I take another point here, it will be T3 and another point, T3 and another point, T3 and the T3. So you can see that at each point you have that T3, the temperature, and here I can take the T3. Okay, again, these temperature values don't change with respect to time, and it is one-dimensional and constant over that area. The same about the T1. Okay, and even what you can do is that you can take another, that random location here. Say that about this location, and here you will have that T2 here. For example, T2 and the T2 here, and you can go in that direction to T2 and the T2. Okay. So here the temperature along this, and that over that surface is also the same, and it is equal to T2. Okay, now let's write the resistance concept for this case now. And if you remember from our previous lectures, we have said that Q dot is constant, and the T was equal to C1x plus C2. Okay, Q dot was constant, and the temperature was C1x plus C2. So it means that if you have the Q dot at inlet, and that Q dot will be the same here. Okay, if it is 30 watts at inlet, and at outlet should be 30 watts. Okay, the same temperatures and the same heat flow, and that doesn't change along this, that with these approximations. Okay, so that Q dot will be equal to negative K A and dt by dx. Okay, and since T is linear, you can see that C1x plus C2, and therefore that dt by dx will be the same as delta T by delta x. Okay, and that one will be equal to that T at temperature 3 minus T1, and divided by, if I take the length of this wall here as L, okay, the thickness actually, it will be that L. Okay, and just replace it here, so it will be that K and into A and T3 minus T1 and divide by L. If you know that to cancel out this negative effect here, so you will have that Ka and T1 minus T3 divided by L. And in electricity flow, so you know that I have a voltage here, which is V1, and I have a resistance here, which is R, and I have voltage here, V2. And I know that the current here that flows over this part in that direction, I, will be equal to V1, voltage at 1, minus voltage at 2, and divide by R. That is the electricity. Now, similarity for the electricity and the heat transfer will be that. So heat flow. So this one is current flow. And for the heat flow, what I will do is that Q dot, which is heat transfer, will be equal to a temperature at 1 minus temperature at 3 here. You can see the similarity. Temperature at 1, temperature at 3, and divide by the resistance. Now here the resistance is due to conduction, therefore I will just add this CD here. That means that it is due to conduction. So, and with this one and with that one, I will build the, I'll just let me write the full equation. Full equation is that T1 minus T3 and multiplied with Ka and divide by L. This is the final form, full form equation, and from here you will just notice that RCD is equal to L by Ka. Okay. This is the resistance. So when heat flows from the temperature 1 and the temperature 3, so when it flows in that direction, it will, you know, that feel the resistance from the wall. And that resistance from the wall will be due to its length or the thickness. This one is L. Let's talk about this one in more detail here. RCD is L by Ka. So that resistance due to conduction is about the thickness. So it means that the more thickness, it means more resistance, R. So if you increase the thickness of the wall here, you will have more resistance, and therefore that you will have the less heat flow. And the second is that the conductivity here, that less conductivity, okay, and then again more resistance. Similarly, area here, so that the less area, so that more resistance. Okay, with this combination, if you increase the, if R increases, then you will have that less Q dot. Okay. Q dot will drop. If you increase the resistance more, you will have the less heat flow, and this is the resistance heat concept for the plane wall here. Now this one is about the conduction. If I talk about the convection part now, let's talk about convection. And from this temperature at, so I just forgot to add this. So you will have that T1 here, you will have this resistance, and you will have that T3, and this is RCD, and here you will have that Q dot. Okay, so here you will have that, let me just show you T1 here, and you will have that resistance inside the wall, and then you will have that T3, and you will have that Q dot. Okay, so this is the general notation that we show for the heat flow. Okay, and you have to remember that heat flows from higher temperature to lower one. Therefore, T1 is always greater than T3. This one is for the conduction. Now let's see the convection part. And for the convection, if you remember the equation, it was equal to H and the AS and TS minus T infinity. Okay, and if I go back to the wall case here, you have that T3 here, which is the surface temperature here. T3 is the surface here. So that TS is T1 and the T3, because this part is also the surface temperature, and this part is also the surface temperature. And you have the environment here, let's say that with a temperature of T infinity. And this environment will have some heat coefficient of H, because this environment takes heat flow from the wall here. So if I write for the T3 case, you will have that Q dot CV will be equal to T3 minus T infinity and divided by, so you will have that the resistance of the CV. Okay. And from here, that RCV value will be equal to 1 by HAS. Okay. Therefore, the resistance in convective heat transfer depends on the convection coefficient of H and as well as the surface area, which is very similar to K and A here. And only the part that you are not considering is this length. Okay. This one is for the convection. And for the radiation part, and this is again from our first lecture, and in our first lecture we have said that the radiation is equal to, you can just simplify the radiation equation with that H radiation, and you will have that AS, very similar to this one. You will have that TS and minus T surroundings. So then you will have this TS here, it will be that T3, and you will have that surroundings. You can notice that here it is T infinity, but it is here T surroundings, because that surroundings may be at a different temperature than the infinity temperature, and you will have the heat transfer between the wall and any object that is outside the wall. Okay, and if T surroundings is same as T infinity. Okay, what it means is that, let me just give you one example, that T infinity is room temperature. For example, it is 20 degrees Celsius, and T surroundings, it can be that table, or it can be that glass, it can be that, that condenser of air refrigerator. Okay, these temperatures are all the same as the T infinity, and then you can just replace the surroundings as the T infinity. But you have to remember that this surroundings is a variable one. And then you will have that H radiation AS, and similar to this one, T3 minus T infinity. Okay, and from here that that radiation RD will be equal to that, similar to this one, 1 by HR AHAS, but this one is H radiation. And if you combine these two terms here, so that Q dot total will be equal to Q dot CV plus Q dot radiation. Okay, and you can just write one final result, that it will be that H CV plus H radiation and the AS T3 minus T infinity. Okay. And from here that R combined will be equal to that 1 by H CV plus H radiation and multiplied with AS. Okay. Okay, you can do this one too, because if you don't want to consider radiation as a different heat transfer, you can just write the combined heat transfer for both of it, and you can just replace the heat transfer from each of it as one heat transfer, and the combined resistance will be 1 by H CV plus H radiation into AS. And here, main difference between the HCV and the H radiation is that H radiation is function of temperature. Okay, if the temperature changes, the radiation heat transfer coefficient changes. But HCV is function of velocity. Okay. If the velocity of the fluid changes, the CV will change. This one is function of velocity, but this one is function of the temperature. Okay. And with this one, so I have just shown the resistance concept, all of it, for the convection, for the radiation. Now what I will do is that I will just write the series concept here. So what the series concept means. So let's just show the series resistance. Let's just show it. So I have the wall here. Okay, I have the wall here, and for this wall, I have the temperature, which is T1 here. I have the temperature 2, which is T2. You can notice that T1 and the T2 is at different temperature. Okay, I have the T infinity 1, and this one means that the room temperature. And I have that T infinity 2, and this one is that outside temperature. Okay, and with this T infinity 1 and the T1, you will have that. So this one is that R combined. R combined, if you remember that, this one means that CV plus R radiation. Okay, combined resistance of this one. Okay, not addition, because if you add it, it will not be the same here. So that this one means that R of CV and radiation together. Okay. And then you will have that T1 and the T2. For T1 and the T2, you will have that this one is the RCD due to conduction, and the T infinity 2, you will have again, this one will be that R combined. Okay. And between T infinity 1 and the T infinity 2, so similar to electricity, I will just draw the electricity one here. So you will have that V1, you can have one resistance here, you can have another resistance here, you can have another resistance here, and the V2. Okay, and the current is the same, which is I, and you will have that R1, you will have that R2, and you will have that R3. And I is equal to V1 minus V2, and divide by the total resistance here. You just add the resistances. Similar to electricity, what you will have is that you will have that the current, which is that heat flow, will be equal to T infinity 1, which is larger one, minus T infinity 2, which is smaller one. So that T infinity 1 is greater than T infinity 2, divided by the total resistances. Okay, and the total resistance is the resistance of CV, or the combined, plus the resistance of CD and the resistance of C combined 2. This one is 1, this one is 2. And if I add it, it will be that 1 by H combined AS1 plus for RCD, it is L by KA, and the plus for the combined 2, it will be that 1 by H combined, this one is 2, this one is 1, and this one is AS2. Okay. This will be the equation, and this will be the heat flow. Okay. And with these equations, now you can solve the heat transfer in a series form. So the example is for this glass. So we have a double pane window here. And for this double pane window, you have the glass, you have another glass, and in between you have the air. Okay. And with the same approximations of 1D, that's steady, and the no heat generation, and the same areas at both sides, the question is to find the heat transfer from this wall here, from this glass here. The values that are given here is that we will need the thickness of this glass here. This one is glass 1. So you have that glass 1 here, you have this glass 2. Okay. And for this glass 1 and the glass 2, let's just write the values here. For the glass 1, let's say that is 3 millimeters, and glass 2, it is 3 millimeters. And in between glass 1 and the glass 2, you have the air. And let's say that this thickness is 10 millimeters. Okay. This is the question, and the question is that what is that heat flow? Okay. And say that T infinity of room, that is 25 degrees Celsius, and H infinity, so that I'm just writing the H combined, so that HCV here, I'll just write the combined heat transfer, and that one is equal to, say that 10 watts per meter square Kelvin, and the conductivity of the air, that is equal to 0.0026. So it should be 10. 0.26 watts per meter square Kelvin. This is the conductivity of air, and the conductivity of glass. Okay, let me just check this conductivity of the glass here. Just 1 minute, that I will just write the conductivity of the glass here. So the conductivity of the glass is 0.78 watts per meter Kelvin. Okay, so this one is meter Kelvin also. So this one is meter Kelvin. Okay, and then you will have that T infinity of the environment. And let's assume that this one is at 0 degrees Celsius, and the H combined of the environment is 20 watts per meter square Kelvin. Okay, and we will also need the glass dimensions, and the dimensions of the window is that window. Okay, and for this dimensions of the window, you will have that 3 meters high and 3 meters wide. Okay. This is the glass, and these are the values that we have got. Another question is that what is the heat flow through this window and with the given values here. Okay, now let's solve it. So I will just start with the resistance concept. On the glass, you will have that TS1, and here on the outer glass, so you can see that we have two glasses here. On the next glass here, you have that TS2, and here you will have that T infinity 1, and here you will have that T infinity 2. Let me just write in a resistance concept. So that T infinity 1, you will have that first, which is the room temperature. So this one is T infinity 1. And then from this T infinity 1, you will have that first resistance. First resistance is that R combined. Okay, this one is room. Then you will have that glass. And the TS glass you will have here. And then you will have that, erase it. Actually, let me show the components first and then resistance concept. Just let me erase it. Let me just show the components here. So you have this glass. Okay, this one is the glass. And you have the air here. Here you will have this air. And you have this one more glass here. And this one is glass too. Okay, and this part is the room, and this part is the environment. Okay, room, environment, glass 1, and the air, and the glass 2. Okay, and let's show the resistance concept now. For the room, you will have this. Let me just write the temperature values here too. This one is that TS1, okay, and here you will have that T2, and here you will have this T3, and you will have that T3, TS2 actually, TS2, and here you will have that T infinity 2, and here you will have that T infinity 1, okay. Now the resistance. From that T infinity 1, from this T infinity 1 to TS1, I will have the radiation and the convection together. So that this one will be R combined, the radiation and the convection. And then from TS1 to T2 value here, you can see the glass part. Here you will only have this RCD, resistance of the conduction. I will just have the air part here now. I will not just write the air part, and I will ask that to you. And then you have the glass 2. And you have glass 1 and the glass 2, they have the same dimensions, but you have to neglect that this part looks thicker than that one. They have the same dimensions, which is that 3 millimeters and the 3 millimeters, okay? And then you have this glass 2 here, again, the resistance of the RCD. And then you have this environment. Okay, and this one will be that R combined, okay? And I will just write the temperature values on it. Here you will have that T infinity 1, and this node here you have that TS1, and next node here which is T2 here, and next node here which is T3, and here you will have that TS2, and here you will have that T infinity 2. And my question comes to that, and this one is RCD, glass 1 is RCD, and glass 2 is RCD2. And what is the resistance of the air? So that R of air. So the question is it CD or is it CV? And the third one is it radiation? And this is the question that's up to you. And let's see what are your answers. So that first option is that the radiation is not true, because that air is a non-interacting medium with the radiation. So if there is a radiation, air doesn't interact with it. It doesn't, that almost absorb it. It only transmits the radiation. Therefore, here we don't have any radiation resistance. Okay, and for the conduction and the convection part, so that if it is convection, so that air should move. Okay, if it is conduction, air should be stationary. And let's see that one here. So that I have a glass one here. And I have the gap here. And then I have this glass too. And this part is the air part. Okay, and this is the thickness that we are considering, which is the case now here. It is that 10 millimeters. Okay, and for this distance, okay, if let's say this one is D. If D is small, so it means that air can't move, because the distance is very small, so that there is no any space for air to create a current, so that, and can't create current. And we call it as the convection currents. Okay. And if D is large, what will happen is that air can move and create current. So that I've just written the current term together 2 times. So if air doesn't move, if D is small, you will have that K value, because it is stationary. If D is large and the air can move, you will have that H value. And the H is greater than the K value. Okay. And if H is greater than the K value, so what means is that if you remember the resistance of the convection, that was equal to 1 by H into A. And the resistance of this one was equal to L by Ka. Okay. As you can see that it is inversely proportional to conductivity and the convection coefficient. So therefore, if H increases, what it means is that RCV drops. Okay. Then this one will not be an insulating medium. It will let the heat flow. But that is not our aim. So that aim is here. Aim. What is our aim? So that you will have that air as insulating medium. So that no heat flow. Actually, it is not no heat flow, but it will prevent heat flow. It should prevent heat flow. Air should prevent heat flow. Therefore, if H increases, then it is against our purpose. This one is against our aim. So we should keep the space very small so that air can't move, and here you will have that more resistance, more R, and here you will have that less R. Okay, and therefore, for the purpose here, the air can't move. That is the design purpose, and therefore it can't be convection. It will be that conduction, because the distance is 10 millimeters and it is very small to create the convection currents. Okay, so here it is very small because it is 10 millimeters. Okay. And for this 10 millimeters, it can't create the convection current. But if it was very large, you would have something like this one. So that you could have, for example, that, let me just show you, you will have these convection currents. Okay, the convection currents will be something like this one. The air, that rise and then touch this surface, it gets cold and it drops, and again it rises. So you will have this convection current here. Okay, but this is not the case. So for large D. Okay. So therefore it will be that CD alone. So that this part will be our CD. Okay, you will have that C combined and the CD and the CD, CD, and then you will have that combined again to infinity. Next lecture, I will continue from this part and I will finish the question. Or if you want, you can solve the question in the break time. So I just stop the recording here.